any ground test, when you can set aero bands and all that sort of thing.
Absolutely appreciate it.
Doesn't work very well in flight.
Essentially, that's,
So we'll talk a little bit about it. Well, when we start getting ready to instrument our airplane, the first step is to measure an instrumentation or get an instrumentation list. Once we know what we're going to test, then we've got an instrument for that specific test. And so and depending on the number of tests we're going to do, well, we need to develop a list that says what we need to measure. And that list is just a catalog of the things that we're going to measure and what the range of values that we expect, kind of accuracy, resolution, frequency response, those kinds of things. Where you're going to put it on the airplane, what kind of environmental conditions is it going to live in? Is it going to have to be next to the engine, or it may be really hot? That's going to require a different kind of instrumentation than one you're going to put someplace where it's nice and cool. So you want to take those kinds of things into consideration. The instrumentation engineer, if you have one, and if you're not filling both of those functions, ought to be brought in to the development fairly early and can tell you a lot of things. Instrumentation is a discipline in itself, and somebody who works in it every day can help you with a lot of things, particularly the cost of the system. You may go to a catalog and find what you want, but there may be something cheaper, I guess is the point. It works just as well or maybe better. So get those folks involved as early as you can. Generally, we have in flight test instrumentation, we have a data collection system and then something a data processing subsystem. Now, you may only have the first one. Okay, depends on what you're doing and how you're doing it. When I worked at Piper years ago, we were doing an airplane called the Cheyenne 3, and they bought this nice automatic system. Trouble was, it was primarily the data processing subsystem that took up all the space in the airplane and wouldn't allow them to load the airplane to centers of gravity that they really needed to get to for testing, because the subsystem, this data processing subsystem, actually took up all the space. Now, all that stuff, has gotten smaller over the years, but the point is, if you're going to spend the money, spend it on the first one. Spend it on the sensor, not on the computer that collects it. Okay, that's the point of the whole thing. The collection subsystem that collects a lot of parameters with high accuracy at low frequency, it's best to use a digital one. And for one that has a few parameters with a high frequency and lower accuracy, a analog system is best. In today's world, we always always think that a digital system is always better. That's not necessarily true. Okay, even though we seem to go that way, sometimes an analog system is much better. The last bullet there, high accuracy, high frequency response, and for collecting a lot of parameters, you end up with a complex, costly, and the last part of the bullet, unreliable system. Okay, be careful about that. And my experience is, I have this thing. I never met an electron I could trust. Okay? It's because of that. Instrumentation systems are the biggest cause of loss of productive flight test flights of anything. That's why I never met an electron I could trust. They break. And I also have a story, a flying story related to that, but I won't bother you with it now. We don't have that much time. That data collection subsystem, consider if all the parameters need to be recorded all of the time. One of the things that the military flight test centers do, which I have complained about, is that they will take an airplane in and they instrument everything in sight. You don't need to do that. You don't need to do that. I mean, if you're only testing a specific thing, just instrument for that. But when you go to them and say, why are you doing all this? Oh, well, we might have an accident. And we want to know, hey, I don't like flight tests that say, well, we might have an accident. Okay? We don't want an accident. Let's plan positive, not negative. But that's the excuse I get when I get that. So you can make the system a lot cheaper and smaller if you don't instrument things you really don't need. Cost of an instrumentation system is directly related to the requirements that you as the engineer impose. And accuracy has the most important influence upon cost. Very high accuracies are difficult to achieve and very costly. Let me give you an example of that. I was doing a 3-month course up at Naval Air Station, Patuxent River, Maryland, which is the Naval Air Test Center. And while I was there, they weren't real happy with my instrumentation system for the course. And so they were going to loan me this instrumentation system that was accurate to 0.25%. So they gave me, and we installed it in my airplane and what have you. And then we were recording it on a 2-inch strip chart that the width of the pin was at least 5%, maybe 10. Don't get fooled by that sort of thing. Let me tell you, when you start wanting accuracies of 0.25%, that gets real expensive. And if you're recording it on a system that at best is 5%, yeah, why did you spend the money on that 0.25% system? But let me tell you, you see that in this business with regularity. So, watch out. Now, one of the things that happens in flight testing, and I'll tell you this from the beginning, the final date of the program is never allowed to slip. Everybody else is allowed to slip. Well, guess where flight test occurs? At the end. So we're expected to make up everybody else's schedule slippage. Can't happen. So you get a lot of pressure. One of the things about flight tests, you'll find there is a lot of pressure in this business, so be ready to deal with it. But when it comes to here, these slippages occur, and we had this much blocked out for flight tests to begin with, and by the time everybody slipped, we've got this much left. Ain't gonna happen, But they seem to think it can. Well, reliability comes about from a good system design, which you play a role in. Good components, a good system checkout, and well, a good system should be maintainable, accessible. You know, you don't want to put it someplace where you have to tear the airplane apart to get to it. And it ought to be flexible. You ought to be able to do several things with it, is what I mean by flexibility. Well, how do we reduce some of our data uncertainty? That's what we deal with. A flight test combines most of the types of errors found in other experimental methods. And I've listed some there: fixed or systematic errors, random errors, gross blunder errors. You can usually call that either that last one either engineer or pilot. Okay, who makes the gross blunder errors? In the pilot's case, oh, we're supposed to do that with the gear down, not up. You know, those kinds of things. I mean, believe it or not, it happens. Or, yeah, well, I thought we did, why won't this airplane accelerate? Well, we've got the flaps down. And here's the other thing, we're gonna have a limited sample size. We cannot get all the data that we want. This costs too much. So we have to come up with some ways of dealing with that. Well, we ought to know where the errors come from. We ought to do all we can to minimize them, and then recognize what remains. And by that, I've had folks who work for me and students come to me with flight test data with 4 decimal places. Ain't gonna happen, folks. You're lucky if the first one to the left of the decimal point is valid, okay? That's the kind of thing you have to recognize. You know, we're not gonna get 4, which reminds me of a story. I had a guy working on his doctorate at my last university, and we were doing this flight test on a little airplane called the Jetwing. It was a little powered lift, single engine powered lift airplane. And this young man, we've been doing essentially flight path angle versus airspeed plots for various thrust settings, which were all straight lines. And he came to me one afternoon with this plot, and you know, there was a point here, a point there, a point there, and then a point way up here. I said, that's a bad point, because he'd drawn this curve that looked like this when everything else had looked like that. Okay. I said, this can't be. This is a bad point. But it came out of the computer. Garbage in, garbage out. Sure enough, he went back and looked, and yeah, he made an error in entering what the thrust level was on that last point. But things like that happen, and you know, if something like that occurs, you got to immediately be a little skeptical of that. Well, what is an error? The difference between the true value and what you measure. Instruments, you look at instruments, you find that they have a couple of different types of errors. Let's see if we can make a little plot here. Let's say we're calibrating an instrument, and this is delta, let's say it's airspeed, delta VI, and this is a value of for the true value, let's say. And we go up and we have points that look something like this. And then we come down and we have points that look something like this. And this is increasing airspeed, and this is decreasing airspeed. Okay, well, the actual value is someplace in between. So if we connect these dots, and like I say, awful drawing on the blackboard, but anyway. That's our calibration. Increasing, this difference between the two is the hysteresis error. Okay, the difference between increasing and decreasing. Now, I'm using this in a flight test. Let's say you were measuring something where you were increasing airspeed. Would you use this center line, or would you use these points? Anybody got any ideas?
You want to be as close as you want to improve.
Okay, if we're increasing airspeed, and these were increasing airspeed points up here on the X's, then we'd use that value. If we were in a stabilized situation where we'd been sitting there for a while, then we'd use the middle. If we were decelerating or decreasing, we'd use the bottom. Okay, so stabilized points, where we were stabilized, we'd use this line, but if we were increasing or decreasing, we'd use the upper or the bottom. We'd use the bottom part of, and decelerating, we'd use the bottom part of the hysteresis, and accelerating, we'd use the top part. And stable points, we'd use the middle, okay? So, hysteresis is the difference between the measure, increasing and decreasing values. Ought to be fairly small. If this spread starts getting real big, probably need to get a new instrument or send that one off and get it overhauled. The bias error is the difference between the correct reading and that one. So this difference right here, that's bias. Okay, so that's the bias error. Well, we start flying the airplane through the air. We're going to talk more about this later. But we flying this airplane through the air. It creates its own pressure field. But what we really want to measure is the pressure way out here someplace that's not affected by the airplane flying through the air. But we can't do that in most cases. We'll talk about some ways that we try in another class. But when we're flying through the air, this pressure field gives us an error between what we read on the airplane and what we read out here that's the true value for pressure. So we depends on where we put the static source primarily, not the pitot probe, not the total pressure, okay, but the static pressure gives us the error, and it depends on where we put that on the airplane. Okay, and that is called position error. i.e. the position where the steady source is, okay? That's how it got its name, a position error. So the airplane itself has its own airspeed error. And, you know, since it's static pressure, it also gives you an altimeter error, okay? Both airspeed and altitude are affected by position error. So we have to use a multi-sample experiment to determine what that is. And what we'll end up doing is we'll end up making another curve of what we call delta V PEC for position correction. And this is VI, instrument corrected indicated airspeed. And we will come up with, you know, a bunch of points where we will determine what the position correction is for that airplane. That'll be the actual first data that we'll get in this class, okay, is determining the position correction for the Cherokee 6. Now, you all will have a separate set of instruments. They're all connected to the same pitot and static source. So you may see some differences, but those differences are not in position correction, they're in instrument correction, okay? But we will calibrate that system. It is going to be different than the one that I'll be flying off of. Okay, the FAA requires us to keep our test system completely separate from my pilot system, okay? So reading the pilots and besides, our test system is much more accurate than that ship system. And I'll tell you why that was the case. Here are some other errors that show up in flight tests, reading or discrimination error. You know, if you're right in front of the instrument, you can probably read it fairly well. If you're off to the side, you've got parallax, and you worry about that. Again, the trace width thing I talked about earlier about, you know, how wide is if you've got an automatic recording device, how wide is the trace that thing is making? It can introduce significant error. Pilot technique, probably the biggest error and the most uncontrollable error in flight testing. Because the pilot may not be trimmed on the correct airspeed, he may be holding some pressure, he or she. You'll get to see both he and she in this course. I won't say I do a better job of flying the airplanes, but anyway. So trim speed, you know, it's nice to be trimmed hands off on most of this stuff. Insufficient time to stabilize. This is the other thing I used to hate when I worked in the industry. I just absolutely hated when the magazine writers came to fly in our airplane. Because the magazine writers would always want to see how fast it goes, and they'd climb to altitude, and they'd level off, and they'd immediately read the airspeed indicator. Well, the poor airplane hadn't had time to accelerate and stable out, you know, so it was always slow. I just hated those guys because the airplane's really slow, you know. Give it some time, jerk, you know. But you know, that was the case. You got to have time for the airplane to stabilize. It doesn't immediately stabilize as soon as you level off, okay? And speed, it takes time. Wrong configuration. This is a pilot technique thing, okay? Yeah. Now you were supposed to do that when flaps up, you know, and you got 15 degrees flaps or what have you. I'm making fun of this, but it's an easy mistake to make, particularly on an airplane like the Cherokee 6, because you've got 3 flap positions. And the last two, one is just about that high off the floor, and if you didn't make sure it went all the way down, well, you still got 10 degrees of flaps out, okay? So wrong configuration, easy to do. Gross blunders, just, whatever. Well, power and thrust, again, reading the instrument, misreading the instrument, that's easy to do too. And the other thing, and we have this problem with the Cherokee 6, we bought this as a used airplane, and so it supposedly has a 260 horsepower engine. But the FAA allows the manufacturer of engines to have plus 5%, when they do their static run with the engine, it can be 260 horsepower plus 5%, or 260 horsepower minus 2%. Well, that gives you 7% possibility, and what the FAA will assume if you don't have a calibrated engine is they'll say, okay, you don't have a calibrated engine, so we're going to assume that the engine that you tested was 260 plus 5%, and that all of those out there in the field